Trigonometric functions. Objective 6 of section 1.2, mathematical models, a catalog of essential functions. Some of those essential functions are trigonometric functions. In calculus, the convention is that radian measure is always used except when otherwise indicated. So our angles, we assume that when you say a number that and it's an angle measure, that it's in the units of radians, not those of degrees. For example, when we use the function f of x equals sine x, it is understood that sine x means the sine of the angle such that the radian measure is x. So input an x, we interpret it as a radian measure, and the output is the sine of x. Okay, so here's the graph of the function f of x equals sine x. Now we see this wave sort of graph. Why is that the graph of sine x? Well, sine x means the sine of the angle whose radian measure is x. Why are these outputs, these y values on this wavy graph, the outputs when the inputs are radian measures of x, x values such as pi over 4, and the output, is this y value here, whatever it is, something a little bit less than 1. We're going to see that it's exactly square root of 2 over 2. But why is that? Well, you have an angle, and that's the x value, right? The angle. So some kind of angle, and we're saying no matter where that angle is, the sine of it is going to be the output of this function. Okay. Well, since it doesn't matter where it is, let's put the vertex at the origin, and let's let one of the sides be on the positive x-axis. And we could take points on either side, maybe on the terminal side, the upper side in this case. We would have to point here. And sine would be, maybe the angle is an angle with pi over 4 radians, which is another way of saying 45 degrees. And, maybe that point is on the terminal side. And so then we would say, okay, what is the ratio of the opposite side and the hypotenuse? Okay. And it would be, a certain ratio. That's what sine is, right? For a right triangle, opposite over hypotenuse. But that ratio is going to be the same as this ratio here. And, it really wouldn't matter where on that terminal side we wanted to plot a point. The ratio would be the same. Similar triangles. So let's just use a point on this unit circle, a circle centered at the origin of radius 1. That way, the length of the hypotenuse is always 1, and the length of the opposite side is, well, it's just the y value And the ratio will also be that same number because you're going to divide it by 1 because it's opposite over hypotenuse. And so sine of that angle, pi over 4, is just this y value here, square root of 2 over 2. And that's why we have this point on the graph right here, pi over 4 square root of 2 over 2, which is approximately 0.707. If we increase the angle to pi over 2, okay, pi over 2, then we would look at the y value, which is 1, and so the output will be 1, which is why we have the point pi over 2, 1 on this graph of sine x. And we could continue throughout getting ordered pairs and getting this wave. And we could go in the negative direction and get angles here that have sides extending into the fourth quadrant, and those ratios will give us negative values. And of course, as we can see, there is blue in this graph of f of x equals sine x below the x-axis, so sine can take on negative values. We could do something similar to get a graph of y equals cos x, the cosine. And so these graphs, these are elementary. We memorize them. And of course, one is just the shifted version of the other. You can tell by the shape. And the length of a cycle, we talk about the period of a trigonometric function. You can see here we have shifted. Cos is the horizontal shift of sine. Notice that for both the sine and cosine functions, the domain is negative infinity to infinity, and the range is the closed interval negative 1 to 1. Right? In the vertical, both of those graphs were trapped between negative 1 and 1. And so for all values of x, sine x is between negative 1 and 1 inclusive. The same is true of cos x. Or we could write it using absolute values. These inequalities are the same. Absolute sine x is less than or equal to 1. The same is true of absolute cos x. Also, the zeros of the sine function, right? That wave, it intersected the x-axis infinitely many times, including at the origin. They occur at the integer multiples of pi. So sine x, right, whatever x value makes that true, is a zero of the sine function. Okay. And we'll just say, okay, let's let x be the number pi, for example. Pi is a zero of sine x. Well, any integer multiple of pi is a zero of sine x. So we could say x equals n pi. Sine x equals 0 when x equals n pi for any integer n. What is the set of integers? The set negative 2, negative 1, 0, 1, 2, An important property of the sine and cosine functions is that they are periodic functions and have period 2 pi. So, we can tell that the graph, it kind of repeats itself after a while, right? I mean, for sine, once it does this, all there is for it to do is to keep doing that same thing over and over and over and over and over as you go to the right or to the left. And that distance is 2 pi there in the horizontal. So periodicity, as applied to the sine and cosine functions, means that for all values of x, sine of x plus 2 pi is the same thing as sine of x. Take any number, you can take any number at all, like 1, okay? Let x be 1. The sine of 2 pi plus 1, whatever that is. Well, whatever it is, it's going to be the same as sine 1 because of the periodicity of the function, okay? When you get to 2 pi plus 1, which is maybe about right there, the output will be the same as it was for sine 1. X equals 1 right here. Then we had pi over 2. And cos also has the same periodicity. The tangent function is related to the sine and cosine functions by the equation tan of x equals sine of x over cos of x. So you take any angle and you get the sine of the angle, you get the cos of the angle, and you do the division, and that's the value of tan. Now, we explained how the sine was just the y value, and it's true that the cos is just the x value. Tan is actually y over x, but keeping it in the white box, we'll think of tan as sine over cos. The graph of tan is shown in the figure. It's undefined whenever cos equals 0. Okay, so if you have an x value that makes cos x 0, now you're dividing by 0, which is, not allowed for real numbers. And so whatever x value does that, makes cos 0, is going to be a x value such that tan is undefined. And you might, I'm sure you can imagine the graph of cos and at pi over 2, cos has a 0. Okay, so when x equals pi over 2, sine has a value of 1. Cos has a value of 0. That's undefined. So for the tan function, there cannot be a point here at x equals pi over 2. And so we have a vertical asymptote. It is undefined whenever cos x equals 0. That is when x equals plus or minus pi over 2, plus or minus 3 pi over 2. All odd multiples, all odd integer multiples of pi over 2. We can also see the zeros there. Those occur where sine, the numerator, is 0, and cos is non-zero. The range, the set of y values, is negative infinity to infinity. You can see how, the entire y, the set of y values is everything, because there's a y value for any number can be a y value. Notice that the tangent function has period pi, a coordinate of some point on this graph. Plus pi is the same as tan x. No matter what x is, so you're going to get the same output for all x. And of course, you can see that period. You can just see that graph repeating itself over and over, and all of those intervals have length pi, right? If you go from negative pi over 2 to positive pi over 2, that's a length of pi. The remaining three trigonometric functions, the cosecant, the secant, and the cotangent, are the reciprocals of the sine, cosine, and cotangent functions, respectively. So sine is the reciprocal of cosecant, cosine is the reciprocal of secant, tangent is the reciprocal of cotangent, and conversely. And so that's a look at some elementary trigonometric functions that we will be using in calculus.